Okay. Theophilus, I see your hand is raised. Do you have a question? Okay. All right. If there's no questions, yeah, why don't we get started? So we're continuing to talk about trigonometry, and we're going to spend more time today talking about the graphs of the trigonometric functions, so of sine and cosine and tangent. But we'll also do some review of how you can manipulate graphs and how graphs change when a function is changed, because understanding these kind of general manipulations about graphs is going to be useful for understanding how to graph some trig functions. Okay, so maybe before we start, just a reminder to everybody to please write your name in the chat so we have your attendance record, so that we know to give you data for next session. Okay, so let's start as usual by going over the homework problems from last time. So Gabriel, by the way, I got your solutions. They're all correct. So thank you for sending them. And actually, Gabriel's, yes, you're here. Okay. Okay, first question. How many radians is 510 degrees? So this is a quick, straightforward question. So does somebody want to give the solution here?
Yes.
Yes. Armstrong.
Okay, so we're asked to find, so how many radians 510 degrees, right?
Mm-hmm.
So calculate, we say 510 times 5 or
Sorry, not getting you right now.
times 5 or
Okay, not getting you so clear, but I assume this is what you said.
You getting me? Hello.
Now I'm getting you, Emmanuel. Hi.
Oh,
But
okay.
Armstrong, I was losing you.
Okay, you getting me clear?
I'm getting you clear, yeah.
Okay. So as you were saying, you multiply degree by pi over 180.
Yeah, so I think. Yeah. So if we want to do this right, I can write the units. Ooh, didn't mean to do that. Right, I can write the units here. This is pi radians divided by 180 degrees, if we want to. And yeah, so Armstrong, you're coming in and out. I'm getting you sometimes and not other times. So do you want to continue? Okay, I'm not getting you now. So
I think his network is having some issue.
So the network may not
Are
be
you
so
getting
good.
me?
I'm getting Emmanuel, I'm getting you fine.
Oh, okay.
Do you want to answer the question?
Yeah, Armstrong is having some issue with his network. Okay. So by that you count degree, cancel degree.
Right.
Okay. Then the 0 can also cancel the 0. So you're left with 510 over 80 times pi over 18.
Right.
So which is 51 pi over 18.
And we can simplify this a little bit more, right? We can
simplify that a little bit. I'm seeing 51 and 18. Should we use 9? No, 9 can go into 8. I think there is no common number between 51 and 18.
So you're right that there's 9 doesn't work, but something smaller works.
Okay.
3, yes.
Yes,
so 3 will work, right? So if we divide this all by 3, we're going to get 17 over 6.
17 over 6, okay.
5, okay. So that's right. Okay. So this is the number of radians. Okay, so this is straightforward. To convert degrees to radians, you're always just multiplying by pi over 180. Okay, so this will let you convert any number of degrees that you want into radians. And that works nicely. Okay, any questions about this?
That's clear.
Okay, clear for everybody? Okay. Okay, good. Let's go to the next problem. So this is a bit more complicated. So a circle has radius 3. And we're going to consider a central angle that cuts out a sector of area 3 pi over 2. So this is radius 3, and the area here is 3 pi over 2, as in the picture below. And so the question is, so if this is our angle theta, is what is the radian measure of theta? Okay. So how do we even begin to approach this question? So we're told something. Remember, radians are defined in terms of arc length. Yes, sorry. Armstrong, are you coming in clearer now? The orange internet better?
Gabriel?
Oh, Gabriel, yes. Hi.
Yeah.
Yep.
I'm trying to know. Am I better off?
Gabriel, I can hear you fine. Armstrong, not so good.
So we can approach the problem.
Yeah.
By first using the area of the setup formula.
Right.
And find the value of theta.
So step 1. Yeah. So area of the circle is what? So the radius is 3, right? Okay. So the area of the circle here is going to be 9 pi, right? Because the radius is 3. And so we have pi times 3 squared, and that's going to give us 9 pi. Okay.
So
Yep. So what do we do next? So does anybody want to say, okay, so the area of the whole circle is 9 pi. The area of this sector is 3 pi over 2. So anybody has an idea what's the next step? Yes,
since
Gabriel?
we already know the area of the setup, find the angle theta.
Right.
So
So how do we find
to
that?
find the angle we can say A is equal to theta over 366 times 9 pi.
Okay, so theta over 360 degrees. Okay, so I see. So theta over 360 degrees times 9 pi is going to equal to the...
Pi over 2.
Right, so that's equal to the sector area, which is equal to 3 pi over 2. Right, because the sector area is 3 pi over 2. So if the whole circle is 9 pi, what fraction of the whole circle is the sector? Well, it's theta over 360 degrees. So let me just write this down. So this quantity here, this theta over 360 degrees, this represents the proportion of the circle occupied by the sector. Right, so whatever the sector is, the proportion of the circle it occupies is theta over 360 degrees. So if we want to know the area of the sector, we take the area of the entire circle, right? So this is, area of the circle. So we take the area of the entire circle and we multiply it by the proportion of the circle that gives us this sector. And that should be the sector area, which we know is 3 pi over 2, right? Good. So we can solve now. So I'm trying to think where to write to solve it. Okay, let's just try to solve it over here, right? So this gives us that theta over 40 degrees times pi is equal to 3 pi over 2. And the pi's can cancel out. And we end up getting that multiply both sides by 40. We get theta equals 3 times 40 degrees over 2, which simplifies to 60 degrees when we solve this. Okay, so this theta over 40, this is just the simplification from canceling out the 9 with the 360. So the 9 cancels out, and we're left with 40 over here. Okay, and then we multiply both sides by 40, and we get 60 degrees. So remember, the question asks for the radian measure of the angle. So instead of 60 degrees, we have to write this in radians. So in radians, what do we get?
Yeah, power.
Pi over 3, right? Exactly. So in radians, we get 60 times pi over 180, and this simplifies to pi over 3. So this is the answer over here. Okay. All right. So okay, so this is the answer. It's pi over 3, but we have to do a couple of steps in order to find the answer, right? First, we have to find what proportion of the circle area is occupied by the sector, and then once you have that, you can set up an equation that equates the sector area with the correct proportion of the full area of the circle. And when you do this and you solve for the angle, you get 60 degrees. Or if we wanted to do everything in radians to start with, instead of writing 360 degrees over here, we could have just written 2 pi from the beginning, right? Because in radians, 2 pi is the entire circle. So we could have had just theta over 2 pi times 9 pi equals 3 pi over 2. And if you solved that equation, it would give you exactly the same answer. You would get that theta is equal to pi over 3. So you can do it with degrees first and then convert to radians, or you can just use radians from the beginning, in which case you would have a 2 pi here instead of a 360 degrees. Okay, but either way works, and either way you get the same answer. All right, any questions on this?
Yeah, okay, that's good.
Okay, thanks. Okay, so the last question, can we simplify the expression sine of x plus 5 pi? Remember, when we're doing trig functions, if I don't write a degrees sign, then it always is assumed that I mean radians. Okay, so can we simplify the expression sine of x plus 5 pi so that it only involves sine of x, so that we can get rid of the 5 pi? Okay, so how do we make some simplifications that will get this to act just like 5 pi? Just like sine of x.
I'm using a different. I'm using some form.
Sorry, it's very, very soft. I'm not getting you clearly. Very soft.
I'm using the some formula of sine.
Yes. Yeah, okay, better now. Seems like got some network problems today. Okay, so what's the first step here? So we have, so actually maybe let me review some observations that we had about these graphs from last time. So this is a slide that we had from last time. So first major observation is sine x and cosine of x are periodic with period 2 pi, right? So that means when you add 2 pi to the argument, it doesn't change the value. So sine of x is the same as sine of x plus 2 pi, and cosine of x is the same as cosine of x plus 2 pi. And that works for every possible x. And then we also have that cosine of x is an even function, sine of x is an odd function, and we have these extra results over here. So sine of x plus pi is minus sine of x, and cosine of x plus pi is minus cosine of x. So yeah, it seems like Orange Network is very bad today. So hopefully it gets better, or if not, we'll still at least have the recording and I'll be able to send the notes. I'm sorry, the network is so so unreliable today. Okay, so given that we have these identities, and really it seems like this one and this one are going to be the key ones to use, right? So it tells us that if you add or subtract 2 pi from the argument for sine, nothing changes, right? So going back to this problem, what do we have? We have that sine of x plus 5 pi equals all right, well, okay, so maybe the networks are not so good. So let me just do this out. Well, the point is you can subtract 2 pi and nothing changes. So this is going to be the same thing as sine of x plus 3 pi. Because when we add or subtract 2 pi from what's in between here, nothing changes. And this here is going to be the same as sine of x plus pi, because I can always subtract off another 2 pi, and it won't change anything. And then lastly, we have that sine of x plus pi here is going to be equal to minus sine of x, right? This is this other property of sine over here, which is that when we add pi to it, it negates the function. So in fact, this sine of 5 pi, if you want to write it without adding or subtracting any angles, it's just equal to minus sine of x. Okay. Okay, any questions on this?
Yeah, yes, sir.
Yes, Prince?
Thank you for the problem stuff. And my concern is this: we have sine parenthesis b s for pi inclusive, and
Yep.
is equal to this equation again, and also equal to this. So where the subtraction you talking about, say subtracting, where it came from? So can it be simply pi here so we can see it?
Right. So, okay, good question. So, right, what's going on here is that we subtracted 2 pi. And then here we subtracted another 2 pi. Okay, and the reason we can do this is that we have this identity that we talked about last time, that sine of x, it repeats itself every 2 pi along the x-axis, right? So sine of x is the same thing as sine of x plus 2 pi, but this works for any x. So for instance, this also works if you're, so for any angle, if you add 2 pi to it, sine is the same. And that means that if you subtract 2 pi, sine is also going to be the same, right? So over here, we have sine of x plus 5 pi. That's some angle, whatever angle that is. We know that if we add or subtract 2 pi to it, the value of sine is not going to change. So to try to simplify this, I'm going to keep subtracting 2 pi to try to get this closer to x. So I first subtract 2 pi, I get x plus 3 pi. I subtract 2 pi again, I get x plus pi. So I have sine of x plus pi. Now, I could subtract 2 pi again, but that would just get me sine of x minus pi, and that's not really any easier to deal with than sine of x plus pi, right? X plus pi, x minus pi, neither one is really better. So at the point that we get here, we need another strategy, okay? And the other strategy is exactly that we have this other identity involving sine from this page. So this other identity, which we saw from the graph and which we'll talk about a little bit more today, is we saw that sine of x plus pi is equal to minus sine of x. Okay, so we couldn't directly apply this to x plus 5 pi, but what we did was subtract and subtract until we got our expression down to x plus pi, and then we use this identity that sine of x plus pi is actually minus sine of x. Okay. So going back to the problem, subtract 2 pi, nothing changes. Subtract 2 pi, nothing changes. And now here, I'm going to subtract pi. And what does this do? This adds a negative sign. Right, so subtract 2 pi, nothing changes. And we subtract 2 pi here, nothing changes. And then here, we subtract pi, and that adds in a negative sign. Okay.
Okay,
All right,
thank
is
you.
that all right?
Okay. Thank you.
Okay. Any other questions? Okay, all right, there's no questions. Okay, so let's spend a little bit more time today talking about all of these different graphs, okay? So let's review the graphs of sine and cosine. I'll start by drawing them here. So we're going to have y equals sine x up here, and we're going to have y equals cosine of x over here. And I'm going to try to draw these graphs kind of the long way. Okay, and last time we drew these using, remember, you can do this all on desmos.com if you want. You can use the desmos.com graphing calculator. Or if you have a graphing calculator, you can use that. But this is just on the internet. And so what I'm going to do is I'm going to mark these axes as follows. Here's pi, here's 2 pi, here's 3 pi, here's 4 pi, here's minus pi, minus 2 pi, minus 3 pi, and minus 4 pi, and here's 1, and here's minus 1. And the graph of sine of 0 is 0. It goes up to 1 when you plug in pi. Then it goes back down to 0 when you go to 2 pi. No, sorry. It goes up to 1 when you get pi over 2, back down to 0 at pi, down to minus 1 at 3 pi over 2, back up to 0 at 2 pi. And then we know once we get to 2 pi, it repeats. So it's now just going to repeat itself. Okay, so it's going to repeat itself now. And then the same thing happens when you go backwards. It goes down and then up. And then it goes up and then down and then down and then up and then up and then down. Okay, so you can verify this on a calculator if you want to, but this is what the graph of y equals sine of x looks like. You have a kind of main part between 0 and 2 pi, and then everything else is just this same thing repeated. If you make a little mark every 2 pi, you can see that between any two sets of red dots, the graph looks exactly the same, right? Up, down, and up, up, down, and up, up, down, and up, and up, down, and up. Right, so no difference there. Now cosine of x, I'm going to do the same thing. We have 1 and minus 1. I'm going to draw it with pi, 2 pi, 3 pi, and 4 pi. And then over here, we'll do minus pi, minus 2 pi, minus 3 pi, and minus 4 pi. So not exactly to scale with each other, but that's fine. So cosine of 0 is equal to 1. So we start at 1. And the cosine graph actually goes like this, goes all the way down to minus 1 at pi, and then up and back up to 1 at 2 pi. Let me level it off a little earlier. Back up to 1 at 2 pi, and then back down to minus 1, and then back up to 1. And then cosine we saw last time is an even function. So cosine of x is equal to cosine of minus x. So that means we have symmetry over the y-axis, right? So in this case, we're just going to have this, and then up here, and then down to minus 1, and then back up to 1. And we have this same idea if we mark the points of the graph above 0 and minus 2 pi and minus 4 pi and 2 pi and 4 pi. So we divide this graph up into chunks of length 2 pi each, then we see that within each chunk, the graph looks the same. It's kind of like down and up, down and up, down and up, and down and up. Okay. So this is the standard graph of y equals sine x, and this is the graph of y equals cosine x. Okay. All right, so we drew these last time. This is what these look like, okay? Okay. Okay, and what we saw, and so then we have these identities that were mentioned last time also. This is just the review. Both sine and x and cosine of x are periodic with period 2 pi. That's exactly what I showed you, that they repeat every 2 pi. We saw that cosine x is an even function. So when you plug in minus x, that's the same as plugging in x. This corresponded to reflection symmetry over the y-axis. I should label my axes. X, y. We have that sine of x is an odd function. So when you reflect over the y-axis, it also reflects over the x-axis. So that what this actually means is rotational symmetry by 180 degrees. It's maybe not quite as easy to see, but if you take this graph and you rotate it around the origin by 180 degrees, it's just going to end up superimposed on itself again. So, so that's something that's true about the sine graph. And then lastly, we have these other identities that sine of x plus pi equals negative sine of x and cosine of x plus pi equals negative cosine of x. Let me just mark that. You know, maybe instead of marking this every 2 pi, I'm going to mark it every pi. So what happens if I mark these graphs every pi? Then what that's saying is that if I take a section of the graph between 0 and pi, if I take the next section of the graph, so meaning I'm adding pi to all of these angles in the next section, the values should be the negatives of what I get over here. And so we see that. I have this section is up like this. The next section, the values take on the negatives. And then the next section after that, the values take on the negatives of these, right? So the negative of this lower arc is a upper arc. And then at the next section, you get the negative again. And the same thing happens with cosine. Let me mark it every pi. So I'll mark the graph at pi and 3 pi and minus 3 pi. Here we have the section of the graph from 0 to pi goes from 1 down to -1. So the next section of the graph should do the opposite. It should go from -1 back up to 1, which is exactly what happens. And then the next part of the graph does the negative of that, the opposite. So it goes from 1 back down to -1. And then the next section of the graph does the negative of that. So it goes from -1 back up to 1. And we see the same thing on the left side of the y-axis. Each section, if you go from 1 down to -1, the next section goes to -1 up to 1. Okay, so adding pi is exactly negating the y value here. Okay, take any section that has a length pi, the next section, the y values are all negated.
Yeah, excuse me, Doc.
Yes, Emmanuel.
So at this junction, where can we identify the period and the amplitude?
Right. So
Is
I
there
haven't mentioned
y
amplitude
equal
yet. So I'll talk about amplitude in a little bit. So right now we're only talking about period. And so the period, you just have to look and see, you know, start from 0. And you just have to look to see how far does the graph go before it repeats itself. So for sine, how far do you need to go on the graph before it repeats itself? Well, I'm going to go up and then down and up. And once I get here, you just have to notice that the graph starts to repeat itself again.
Okay.
So the period is going to be the first x value that you hit where the graph repeats itself. So that's going to be 2 pi.
So that
we'll
means
talk-
it happened. So that means it happened both at the positive and at the negative.
Exactly, yeah. So you have to check that that works everywhere. But this little segment that has length 2 pi is repeated in both directions forever. It's repeated in the positive direction, and it's also repeated here in the negative direction.
In the negative
Yeah,
direction.
so for it to be periodic, it repeats everywhere in both directions.
Periodic.
So we'll discuss amplitude a little bit later. No, we'll do it today. Okay, other questions? Okay, so good. All right. Okay, so let's move on a little bit. So maybe I should make one more observation because Emmanuel talked about amplitude, is that both graphs are contained between y equals 1 and y equals -1, right? So they're what's called bounded functions, okay? They don't go off to infinity. Everything's contained between y equals 1 and y equals -1. I'll draw those lines on the graph. We have y equals 1 up here, and then y equals -1 down here. Right, and ditto, y equals 1 up here, and y equals -1 down here. Okay.
Hello.
Yes, hello? Yeah, Emmanuel?
I'm observing that the y equals sin x and the y equals cos x look a little bit identical.
Yep. Right. They look almost
Okay.
exactly the same. The only
Mhm.
difference is there's a little shift from one to the other.
Okay.
So if you have this graph and you move it over by pi/2 to the left, then it will, so you move this peak so that it's over here instead. So it's on the y-axis. Then you exactly have the cosine graph.
The cosine graph. Okay.
Yeah. And
Thank
so
you.
this
Thank
this happens to be related to the identity that sine of x is equal to cosine of x plus pi/2, which we'll talk about in a little bit. So this is a good question because these graphs look almost identical. In fact, one is a shift of the other. And I did this very quickly last time, but I want to talk today in a little bit more detail, a little more carefully about how graphs can be related to each other. Okay. So that'll be a good introduction to the next part. Okay. So for now, let's just talk about, forget about sine. Let's forget about cosine. Let's just talk about graphs in general. So let's say we're given a graph of a function, y equals f of x. And now let's say that a is a positive real number. So the question is, how do these following graphs compare to the original graph? Okay, so there's these four things we could do to a graph. We can look at f of x plus a. We can look at f of x minus a. We can look at a times f of x. And we can look at f of ax. Okay, so if you think of f of x as like sine x, this would be like sine of x plus pi, or sine of x minus pi, or 3 times sine x, or sine of 2x, right? Depending on what your a is, right? So we have these four different modifications. Let's start with number 1. So the point here is that if x comma y is on the graph of f of x, maybe I should say of y equals f of x, then what happens? Well, then x minus a comma y is on the graph of y equals f of x plus a. Right. Why is this true? Well, xy being on the graph of y equals f of x means that y is equal to f of x. So what about this new point? If we have x minus a comma y, why is that on this graph? Well, let's plug it in. The point is that, so maybe I'll say y. Well, so I'm looking at y equals f of x plus a. So the left-hand side is equal to y. And the right-hand side is equal to f of, well, I have to plug in x minus a plus a. And this is equal to f of x, because x minus a plus a is equal to x. And this f of x, we already said, is equal to y. That says that f of x is equal to y. Okay? So this shows us that if I plug in the point x minus a and y to this new graph, that it actually lies on the graph. If I plug in x minus a for x and y for y, then this equality holds. And so what that tells us, so the upshot is that the graph of f of x plus a is the original graph. All right, so the original graph xy, the new graph has all the same points except you subtract a from the x coordinate. So that's the same thing as shifting the graph to the left by a. So this graph of f of x plus a is the original graph, but shifted a units to the left. Okay. So if you add a to the argument in the x, then it in fact shifts the graph to the left. And I'll say similarly, so say for 2, similarly, which I'm going to leave as an exercise. I'll say that the graph of f of x minus a is the original graph, but shifted a units to the right this time. Okay, so for this reasoning, if I add a to the argument, it turns out that the new points on the graph, instead of being xy, the new points of the graph are x minus a comma y. That's what satisfies this equation. And so that means that all the new points are shifted to the left by a. Number two, which is the opposite thing, everything is shifted to the right by a. Questions on 1 or 2 before I start to do 3 or 4? So these things are going to be important for all sorts of graphing things, not just for trigonometry, although we'll use it today for trigonometry. Okay. All right, so if that's fine, let me just do the other 2 parts. So number 3, we'll say that if xy is on y equals f of x, then we multiply it by a. Well, then x ay is on y equals a f of x, right? Because if one side is y and one side we would plug in ay for y, we get ay, and on this side we have a f of x, which is also ay. Okay, so what this tells us is y equals a f of x is the original graph stretched vertically by a factor of a. Okay, so this is not so surprising. If I multiply f of x by 2, then everything gets stretched vertically by a factor of 2. Okay? It's the original graph stretched vertically by a factor of a. Because instead of having the points xy, we now have the points xay. All the y values are multiplied by a. Okay, so that one's pretty straightforward. Number 4 is a little less straightforward. I'll need a new page to do number 4. So let's just say number 4 here, which recall is y equals f of ax. Well, if x comma y is a point on y equals f of x, then it turns out that x over a comma y is a point on y equals f of ax. Again, you know, what we're doing here is we're plugging everything in. Maybe I'll illustrate this. We're plugging in y for y, and we're plugging in x over a for x. And what we end up getting is y equals f of a times x over a, which is f of x. So we plug in x over a here, we get y equals f of x. So that's going to be the original graph. So what this tells us is that if x and y are a point on the original graph, then x over a and y are a point on the new graph. That means the x values are getting compressed by a factor of a. So I'll say, so the graph of y equals f of ax is the original graph compressed horizontally compressed horizontally by a factor of a. Okay, so these 2 things look very similar, number 3 and number 4. right? Number 4 says y is f of ax. That compresses horizontally by a factor of a. Number 3 is almost the same, but we have y equals a f of x instead of f of ax. And in that case, you get a very different effect. You get stretched vertically instead of compressed horizontally. Okay. So these are kind of the 4 basic things that you can do to graphs. You can shift them to the left or shift them to the right by adding or subtracting from the argument, or you can stretch them vertically, or you can compress them horizontally. Okay. You could also do like y equals f of x and then plus a. That will shift you up and shift you down. But for trigonometry, we're not really going to be doing that so often. So I'm not going to discuss those transformations now. Okay. Okay. So these are all things that you can do with graphs. It's probably worth just memorizing this. Going through and re-deriving this every time is probably, more time than you need to spend. So I would just memorize, like doing x plus a shifts you to the left, x minus a shifts you to the right, and so on. AF of x stretches vertically, f of ax compresses horizontally. Okay. Okay, so these are our graph modifications. So what's an observation from last time? So this is what Emmanuel said. So the graph of y equals sine x comes from moving the graph y equals cosine of x by pi over 2 to the right. Right, let's look over here. Right, we have y equals cosine x here. If we move it by pi over 2 to the right, then this peak goes from x equals 0 out to x equals pi over 2. That's exactly what's happening with the graph of sine, right? So if we go back, we observed this last time. So in terms of equations, this means, what does it mean? Well, pi over 2 to the right is what? That's moving to the right is number 2, right? So if you have an original graph, to move it to the right means that you're plugging in x minus a instead of x. So to say what that originally means, it means that sine of x is equal to cosine of x minus pi over 2. Okay, because what this tells us is that sine graph is the shift of the cosine graph by pi over 2 to the right. Now, it means that if I take my cosine graph, but I now plug in x minus pi over 2 instead of x, that shifts the graph to the right. And so we see this graphically. And so, and in fact, we'll prove next time that this is in fact true, that sine of x equals cosine of x minus pi over 2 using what we call the subtraction formula, or subtraction formula. Okay, so we'll prove this just using algebra next time, not using any graphs. Okay. All right, any questions here about this observation? Okay. 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 All right. So let's go to the next slide. Okay. So some questions. So knowing only what we know about the graph of sine and cosine, can we determine whether tangent of x is an even or an odd function? And can we do that without even drawing the graph? I wanted to see this. Okay. So, and then knowing only what we know about sine and cosine, let's prove that tangent of x plus pi equals tangent of x. Okay, so number one, well, what do we know? If we want to know whether tangent of x is an even or odd function, well, that means we have to understand how tangent of minus x relates to tangent of x. So, well, if I take tangent of minus x, well, I can write this in terms of sine and cosine, right? This is sine of minus x divided by cosine of minus x. And now we have our identities. If you remember, sine of minus x was so sine was an odd function. So sine of minus x is minus sine of x. And cosine was an even function. So cosine of minus x was cosine of x. This is because this is an odd function. And here is because this is an even function. Okay. And well, now sine over cosine is tangent, so this is the same thing as negative tangent of x. Okay. So what we have is that tangent of minus x equals minus tangent of x. And so that tells us that tangent x is an odd function. Okay. Is that okay? Okay, let's look at question number 2. Similar type of question. Let's prove that tangent of x plus pi is equal to tangent of x everywhere where tangent is defined. Well, we're going to do the same method. So what is tangent of x plus pi? Well, the general method in trig is just relate everything back to sines and cosines, right? So this is sine of x plus pi divided by cosine of x plus pi. And well, we have our identities left over from this page. Sine of x plus pi is minus sine of x, and cosine of x plus pi is minus cosine of x. So I'll use both of those identities. So that is minus sine of x divided by minus cosine of x. And then the minuses cancel each other out. And I'm left with sine of x divided by cosine of x. And that's exactly tangent of x. And so we see that tangent of x plus pi equals tangent of x, right? And so an upshot of this, that the tangent graph has period pi, not 2 pi. Okay, so the tangent graph repeats itself faster than the sine and the cosine graphs do, right? So the tangent graph repeats itself every time you move pi over, whereas sine and cosine only repeated themselves every time you move 2 pi over. Okay, that's because the sine becomes negative when you add pi and the cosine does also. And so when you take their ratio, nothing changes. So we have that tangent of minus x is minus tan of x. That's an odd function. And tangent of x plus pi equals tan of x. So it has period pi. All right. Any questions?
Hello?
Yes, Emmanuel?
I have a concern that is, instead of doing the practice on the actual graph, but we are doing it on the literature, so it kind of
Well, we're going to do the graph. We're going to do the
Okay.
graph on the next
Okay.
page. Yeah, we're going to do the graph.
Okay.
But I want to
Okay.
say, like, we can learn some things about the graph without actually graphing it.
Okay.
So this is
Okay.
something that we know when we're going to draw the graph that's going to have these properties. It's going to help us draw it.
Okay.
Okay. So no, we're going to draw the graph. We're going to do that today. Okay. So, all right. So by looking at the graphs of sine and cosine, we're going to attempt to graph y equals tangent of x. And let's remember these things that we did before. So tangent of x plus pi equals tan of x for all real numbers x. That means we only need to know that we only need to know what the graph looks like between 0 and pi. It's just going to repeat itself, right? And in fact, it's good enough. You don't have to know it between 0 and pi, but it's good enough to know it on any interval that has length pi. So it doesn't have to be 0 to pi. If I know it from, minus pi over 2 until pi over 2, that's an interval with length pi, from minus pi over 2 to pi over 2. The total length is pi, and that's good enough. If I can graph it there, then I can still repeat it every time. As long as I have an interval whose length is pi, if I graph it in that interval, I can then just repeat to graph the entire thing. So in fact, here it's good enough to know the graph of y equals tangent of x for x between minus pi over 2 and pi over 2. And just for matters of time, this is going to be a bit easier. Because what happens here? If I'm going to try to graph y equals, well, actually, do I want to do it over here? Okay, let's, maybe I'll not do this here. So what happens if I try to do the graph from y equals tangent of x? Well, let me put pi over 2 here and minus pi over 2 here, right? So if I want to do this graph, well, in fact, I only have to go from 0 to pi over 2 because I know that tangent is an odd function. So whatever happens here from 0 to pi over 2, the opposite is going to happen between 0 and minus pi over 2, right? It's going to be whatever I have here going, I'm going to just get its negative between 0 and minus pi over 2 because it's an odd function. So if you go back, remember our special values. So tangent of 0 degrees is equal to 0. I'll do everything in terms of radians. Tangent of 30 degrees is tangent of pi over 6. This was equal to root 3 over 3. It's about 0.588. So tangent of 45 degrees, which was tangent of pi over 4, this was equal to 1. And tangent of 60 degrees, which was tangent of pi over 3, this was equal to square root of 3. That's a little bigger. And what happens? Well, as x goes to 90 degrees or pi over 2, what happens is that the tangent of x is equal to sine of x over cosine of x. Well, what happens as x is going toward 90 degrees? Well, sine of x is going to 1, and cosine of x is going to 0. So it's a fraction where the numerator is going to 1 and the denominator is going to 0. And so in the limit, what you see is that tangent actually has to go to infinity, right? It's not going to be a bounded function like sine and cosine because it's given by this fraction where the numerator goes to 1. That's fine. But the denominator goes to 0. When x is really close to 90 degrees, cosine of x is a very, very small number. So this fraction is going to be huge. And the closer x gets to 90 degrees, the smaller and smaller this denominator gets. And this fraction gets bigger and bigger and bigger. So what this says is that as tangent x goes to 90 degrees or pi over 2, tangent of x goes to infinity. And in fact, you can't even plug in pi over 2 because you get 1 over 0, which is undefined. So for graphing this, I'm going to draw an asymptote here, a vertical line at pi over 2. And what happens with the tangent graph is that it just goes up toward this vertical line, like this. Okay? And now I claim that once I know this part, then I know all of the rest of the graph, because whatever happens between 0 and pi over 2, the negative has to happen between 0 and minus pi over 2, because tangent is an odd function. So if this is what it looks like here, then it has to look like this over here. And then I know that this just repeats every pi. So I can put another thing here at 3 pi over 2, and another thing here at minus 3 pi over 2. Let me just draw that in blue instead. So in minus 3 pi over 2. And this section of the graph, which has width pi, I'm going to write that here. So the length, I'll call it length, is pi. So because tangent is periodic with period pi, you're just going to have exactly the same thing happen again. So I'm just going to go here and then down here. This, where it crosses the x-axis, is at pi. So we have that. And then likewise, we're going to go up to here and then back down to here. And where it crosses the axis here is going to be minus pi. Okay, so we've gotten the entire graph of tangent. I mean, and I can keep drawing it over and over again. It's just going to keep repeating itself. I won't do that here. But the moral is that because of this work that we did over here with tangent of x plus pi equals tangent of x, and this business about being an odd function, tan of minus x is equal to minus tan of x, that sufficed to get just one small section of the graph of tangent, that part between 0 and 90 degrees, which is the part we already know just from right triangle trigonometry. We don't need any unit circle or anything like that to know what happens with tangent between 0 and pi over 2, 0 and 90 degrees. And from this, we can extrapolate the entire rest of the graph. So we have the negative part over here, and then once you have something of length pi, then you know it just repeats itself every time you move it over by pi. So for the last thing to show you, let me just show you this on Desmos. So let me share my screen here. What do I want? Yeah. Okay, so let me share this on Desmos. What about here? Working here. Sorry, the computer's going slowly. What is going on here? Sorry, my computer's very slow here. Okay, let's try a new tab. Okay, so let's go to desmos.com. Okay. I'm going to go to desmos.com. I'm going to do the graphing calculator. And if I go here, I write y equals tan of x, then boom, you see this graph, right? So this is exactly the graph that I drew. It's got all of these different parts. They repeat every pi, and it even has some special points marked. So you've got the point 0, 0. Here you have pi comma 0. You see it's about 3.14 over here between 2 and 4. Here you have 2 pi comma 0. That's roughly between 6.28. Pi over 2 is about 1.57, so it should be a little bit to the right of this bar right here, because this is 0.5, 1, and 1.5. And so if you follow this up enough, then you can see that, it ends up moving kind of closer here to 1.57. So yeah, with Desmos, you can zoom out as much as you want. You can see what the graph looks like. It's just the same thing repeated over and over again. Or you can zoom in a lot. If you really zoom in a lot, this thing just starts to look like a line. If you've studied any calculus, what this is really is just the tangent line at that point. So maybe if we do our calculus course next year, then we'll talk a little bit more about this. But yeah, so here it's nice. You can see things, you can drag, you can look at a different section of the graph if you want. Here they look like vertical lines. So, it's nice to, go play around with Desmos. But the point is, we didn't need this computer to tell us this. We were able to get everything that we needed by just using the reasoning from even and odd functions and this periodicity. Okay. Okay, so let me stop the share. Let me reshare my iPad. Here. Okay, good. Okay, so this is what we have, so I can say, for fuller graph, check desmos.com. Okay, so, all right, so that's it for today. So for homework exercises, I want to ask similar things. So knowing what we know about sine and cosine, can you determine whether cotangent of x, secant of x, and cosecant of x are even or odd functions? And the question is, I want you to do this without drawing the graphs. So do this only using the type of reasoning we used over here to determine that tangent of minus x was an odd function. Okay? So can you determine whether cotangent of x, secant of x, and cosecant of x are even or odd functions? Number 2 is find the smallest positive number alpha such that cosine of 2x equals cosine of 2x plus alpha for all x. So this number alpha is what's called the period. So it's saying if I take the graph of cosine of 2x, how quickly does it repeat itself? What can I plug in for x by adding something that will make this graph repeat itself? Can you find the smallest number alpha that does that? And then, oh, that shouldn't say question 4. That should say question 2. So here we have the same question, but now for the function cosine squared of x instead of cosine of 2x. So what is the smallest positive integer alpha such that cosine squared of x equals cosine squared of x plus alpha for all x? Okay, sorry, and this shouldn't say integer. Sorry, this should just say number. Okay, smallest positive number. Okay. Okay. So those are the homework questions for this time. And so we have a lot of time because it's going to be 3 weeks until we meet again. So there's no class next week, March 15th for the holiday, and no class March 22nd because I'm going to be away. So the next class is going to be on March 29th, and we're going to discuss some more advanced trigonometry identities. So in particular, we're going to discuss the addition formula. So, formulas for sine of a plus b and cosine of a plus b, and then other things that you can derive from those. Okay, and these formulas are pretty difficult to prove. Okay, the answer is not sine of a plus sine of b. It's more complicated. It's sine a cos b plus cos a sine b. But where do you come up with that? So we're going to do a proof of these formulas based on geometry, and then I'm also going to show you a proof based on matrices for people who know some matrices, maybe who were in the class when I talked about the linear transformations and the rotations with matrices. Then I can show you a formula for this, a proof of this based on matrices. So I'll do both next time. Okay. Yep, so that is what's coming up. So thank you, as always, for your attention and your participation. And I will miss you for the next couple of weeks, but I will see you again at the end of March. All right, and any questions anybody has, I'm happy to take them. And I'll stop the recording.